Hello guys, welcome back. Today I'm going to continue working on my CPU, a RISC-V CPU, which I'm trying to build in Vivado with SystemVerilog. And so, without further ado, let's get started working. So I'm going to start opening Vivado. If the music is too high, just tell me so that I can decrease the volume. No, right? Okay. Okay. Actually, don't like this music. I'm gonna change that. Okay. So we're trying to make us a small multiplexer. I actually don't know why the font is so ugly in Vivado, but maybe I'm just going to go with seed. If I can actually see the sources. Yes. So we're gonna Verilog. Okay, so we need to install the Verilog extension. Yep, Verilog and SystemVerilog. Great. Okay. So I was trying to learn how Verilog and SystemVerilog work. Let me open the repo because I saved some links. No, I did actually not do that. Whatever. I'm just going to use mainly AI because I find it super easy to learn a new language. Making some examples directly with AI. So right here I'm opening the Gemini Fly. I'm going to put 3.1 Pro and I'm going to say hello. I am trying to make a CPU from scratch. I have experience in VHDL, but have known in Verilog and SystemVerilog. Look at nukes.v. Is this a modern way? Because I know it's not. This should be the old way of creating like a multiplexer. I think I'm just going to open some sort of whiteboard or something. I don't know. Draw IO. No, I just want to draw. Okay. Yeah. So let's see if we have multiplexer actually. We don't. There should be electronics and electricals. Yes. Apply. Do we have also some other? Okay, whatever. I think this is fine. So if I try to search for multiplexer, okay, I can just do it with I need a trapezoid, which I'm not seeing right now. Here. So a multiplexer is something like this, where you have no, just move it. How can I move it? You have one line which is controlling the multiplexer, then you have other two lines other two signals, let's say, which are entering the multiplexer, and the job of the multiplexer is based on the control signal. You want to select one of these two signals here. So let's say here, if I can I write here? Yeah, A. Yeah. B. Yeah, let's call this, I don't know, control. So based on this control bit, you want to select A or B, and A or B is going to get like sort of bypassed into the output. So this is what I want to do. I know how to do it in VHDL, which is another hardware description language, but I don't know how to do it in Verilog. So I started with this code, which should be the old way of doing it, because Verilog is an old language, but there should be a better way to do this with SystemVerilog, which is a superset of Verilog, which introduced many new features. Is this the modern way of actually doing it? Doing a multiplexer, or does SystemVerilog introduce better alternatives? Load code mentor, which is a skill I created for Gemini to act as a mentor and not provide like not edit files automatically without my consent, and just trying to be a sort of Socratic mentor. Load code mentor and create and act like SystemVerilog / Verilog expert teacher, which is going to teach me the language while I am making my CPU. So let's see what comes out of this. Yes, let's load code mentor. If you're interested in the skill, you can find it in my GitHub. Maybe I'm going to also write this in the comments. sorry, in the video description. So, welcome to SystemVerilog. Designing a CPU from scratch is an excellent way to learn the language. Since you already have a solid foundation in VHDL, you're going to pick up this very quickly. You already understand digital design concepts. Just need to map your VHDL mental models to SystemVerilog, syntax and semantics. So let's see. I'd love to save your background, okay, because these skills, it's actually it asks you what's your background so that it can tailor the answer to you, but we don't care now. Your Mux.Vico is perfectly valid Verilog 2001. In fact, it looks exactly like what a traditional Verilog textbook would teach you. The always at block is analogous to a VHDL process. So this is the sensitivity list as we saw the last time. And yeah, so basically what we are doing, we also saw that this sort of writing here, it means that I don't remember exactly. This is the base, so this should be base 2. This one, it's the size of the number, and this is the number. So this should mean is select the wire equal to 0 in binary with size 1, so a bit, the bit 0. If so, then select A, otherwise select B. Yikes, yeah, this is a multiplexer. However, SystemVerilog, which is an evolution of Verilog, introduced several powerful features to fix some on Verilog's historical critics and make RTL design much safer and more expressive. The wire versus register confusion. In older Verilog, you had to declare outputs as registers if you assigned them inside an always block, like a VHDL process, and wire if you assign them continuously outside a block. Okay? This is purely a simulation artifact and causes a lot of headaches, which makes sense. It's very strange. SystemVerilog introduces logic. Think of logic as a close equivalent to VHDL standard logic. Yeah, you can use logic for almost everything, whether it's driven procedurally or continuously. Okay. While it always adds sensitivity list so everything works, it doesn't strictly enforce that the block must be combinational logic. SystemVerilog introduced always comb. This block explicitly tells the synthesis tool and the simulator, I intend for this to be purely combinational. This is cool actually. I'm not really sure that we have something like that in VHDL. Probably yeah, but it's cool if you want to enforce that a block needs to be only combinational. Continuous assignment. For something as simple as a 2-to-1 MUX, a procedural block is actually a bit verbose. Just like VHDL has concurrent signal assignments, so y equals b when select equals 1, else a. Verilog and SystemVerilog have continuous assign statements combined with a ternary operator. Based on those SystemVerilog improvements, let's update our code. How would you write the ports of your model to use a SystemVerilog logic data type instead of wire and register? I don't know. Stupid motherfucker. I don't know because I don't know SystemVerilog. SystemVerilog, so you should provide examples, at least for now. Moreover, what is the extension name of a SystemVerilog program, because I will create one in right now. So the meantime, let's close this because we don't need it anymore. Let's try to create a new design source here. Yep. Create file, and we're going to go with SystemVerilog. File name mux. So it's SV. Okay. Yep. Let's go. Nice. There's this mux SV now that we can open. There's also this timescale here, which I don't know what it is. I think it's for simulations. Okay. So the file extension is sv.sv. Okay. Let's look at how your 2-to-1 mux translates into modern SystemVerilog. The procedural approach. Yeah, let's do this because it's similar to the other. So of course we have 3 inputs. And there is logic. This is the of type logic. Okay. Input logic B. Input. It's strange. Okay, so logic. Wait. Can I get info? How can I get info here on it? Just logic. Let's see this logic type. SystemVerilog standard specifies that signals in a design possess both a type and a data type. The type designates whether the signal is a net or a variable, while the data type defines the value system of that net or variable, which are 0, 1, x, or z. Types that can have an unknown. So you're a bit confused about this. SystemVerilog specifies a signal possesses both a type, so for example logic I would say, and a data type. Okay, I'm very confused about this. But let's move forward. Types that can have unknown eigenpedance value in addition to 0 and 1 are called four-state types. In Verilog, all nets and variables use four-state values. Note that reg can only be driven in procedural blocks like always and initial, while wire can only be used in assign statements. Okay. SystemVerilog introduces a new four-state data type called logic that can be driven in both procedural blocks and continuous assigned statements. However, a signal with more than one driver needs to be declared a net type, such as wire, so that SystemVerilog can resolve the final value based on strength. What the fuck is strength? Okay, we're going to read that later. I like this website. So let's see here. We have a module which declares a logic 4-bit type variable somehow. Somehow this is a variable. And then did we also write module here? One bit logic type variable, okay. Okay, cool that we have this display, which with a format similar to a printf, I would say. So default value of logic type is x. Then here they change the value of my data to the value b in hexadecimal. Okay, I don't know what's this. And then again, logic data can also be driven via assign statements. Okay, cool. Let's also read about this Verilog strength. The strength of a driving net refers to the relative power or capability of a driver to influence the value of a net. Two types of strengths can be specified in a net declaration. Charge strength. Charge strength is specifically used with a 3-reg nets. So I guess this is some sort of 3-state buffer to model charge storage. It indicates the relative size of the capacitance associated with the net, indicated by either small, medium, or large. What the actual fuck? This strength determines how quickly a charge can decay on the net when it is not actively driven, allowing for more accurate simulation of real-world behavior in circuits that involve capacitive elements. The default charge strength of the 3-reg is medium. This is super cool. The simulation time for a charge decay should be defined in the delay specification. 3-reg, A net, strength medium by default. 3-reg medium, charge decay time of 100 time units. Okay. Large, strength large, no decay time. Okay. Drive strength. Drive strength refers to the capability of a driver to influence the value of a net. It indicates how strongly a signal is driven on the output terminals of a gate or net. Drive strength is crucial in resolving conflicts when multiple drivers attempt to control a net. The net will take on the value from the strongest driver, and if there is a conflict in values from drivers of the same strength, the result will be unknown. Okay, so there is some sort... Is it like there is some sort of way to prevent short circuits by saying which driver is stronger? I'm not sure. When using the assign statement, you can specify the driving strength explicitly. The syntax for this is assign strength 1, strength 0, net expression. The strength when the net is driven to logic 1. The strength when the net is driven to logic 0. If no strengths are specified, the default drive strength is typically strong, which means that the net will take on the value from a strong driver if multiple drivers are present. If multiple drivers with different strengths attempt to drive a net, the net will take on the value of the strongest driver. If two or more drivers have the same strength but different values, the result will be unknown. Okay. What the fuck? In this example, A and B evaluates to 1. Okay. Out will be driven with a strong signal. If it evaluates to 0, it will be driven weakly. Okay. This is very strange. I'm not going to look into this right now, but it is quite interesting, to be honest. So yeah, let's start. We will look into the logic data type. I think I'm going to look into this tutorial here because it looks really cool actually. But yeah, for now let's continue with this. Okay, so the end module goes at the end. This is interesting. It's a bit different than VHDL, where you need to close the entities. So always comb is a combinational process, some sort of combinational process. You're not going to use registers. So, and in this case it's the same as before, let's say, just that now we have a logic data type. One, the base is binary and the value is 0. Okay. Begin, yeah. You can also use equals, which is cool. And go here. Else, begin. And here we have y equals b. Okay. This is kind of cool, to be honest. Okay, wait. Let me do this. Yeah. So, what if now... Okay, otherwise here it says that you can also use a conditional assignment, which I'm going to do because this looks very ugly for just a multiplexer. And this is called continuous assignment. So, assign equals select so this means if select equals 1, then output B, otherwise output A. So this is exactly like the syntax in C. So this is very fine. What is this assign keyword? Can we see here maybe? Okay, I'm gonna ask Gemini. So, what is the assign keyword doing? Can I not just write the statement? Then I want to create a test bench for this in VHDL. How can I do it? And what would the syntax of the test bench. Moreover, what is this timescale command? What is this timescale command? Of mix.sv. Yikes. So at this point I'd say we can remove the Verilog file. Yep. Nice. Go again and create a new file called mux.sv and try implementing. No, okay, this was the old one. It's still answering. Okay. In the meantime, I'm going to read this. Okay. Wait a second. Okay, yeah. I used commas here. Should I use... Right. Okay. But here... Ah, yeah, this is a test bench. Okay, got it. Okay, cool. I think I'm going to go for a short break, then going to come back soon. And welcome back, guys. I'm back. So let's continue working on our module. Gemini replied, so let's see what it said. I asked that I wanted to create a benchmark in Vivado, so let's see how we can do that. You've asked 3 excellent questions. The assign keyword, why can't you just write? Yeah. In SystemVerilog, the space inside a module but outside of an always block is in the concurrent word. Okay, everything here happens in parallel. The assign keyword is required here to tell the compiler this is a continuous concurrent assignment. Whenever the right hand side changes, instantly update the left hand side. Okay. If you just wrote y equals whatever, the compiler wouldn't know if you meant it to be a continuous assignment or if you accidentally left out the always com block that makes it procedural. In VHDL, you don't need a keyword for this because the context implies it, but Verilog requires a sign. What the fuck? I'm very much confused. It just said that the space inside a module but outside of an always block is concurrent. So what's the problem? I still did not understand what the problem that assign solve is. Because if I am outside of an always block, then yeah, it is concurrent. So why do I need to specify it? I need to specify it. Then the timescale directive you saw, timescale 1 nanosecond, 1 picoseconds, is a compiler directive indicated by the backtick. Also, this is also a compiler directive. I don't know. The first part is the time unit. If you write 5 in your code, relay for 5 units, the simulator knows you mean 5 nanoseconds. Okay. The second part is the time precision. This is the smallest tick the simulator will keep track of. It dictates how rounding happens if you have fractions of a time unit. Okay. A test bench in SystemVerilog is just another module, but with a few key differences from the side module. It has no ports, nor inputs or outputs because it's the top level of the simulation. It uses logic for the signals that will connect to your design. It uses an initial block, like an always block, which loops forever. An initial block runs exactly once at the very start of the simulation. This is where you write your procedural test stimulus, changing inputs, waiting for a few nanoseconds, changing them again. In Vivado, you create a simulation source file. Okay. Okay, let's try. So let's create a simulation source. Already did it. Okay, so I need to remember after to also update the .gitignore file, because right now all these files are not tracked. I don't care about some folders, but others I need to track them. So if I go to sources, no, sorry, I need to go to sim. It should be here. No. What are the files? Simulation sources. Where is this file? It's here. Sources 1 new. Okay. No, we need to move that. We need to move that to another place because this is not a simulation file. Oh yeah. Oh wait, it is. What? What is happening right now? Okay, I just need to create a new file. How do I call it? Test benchmarks. Okay. So, add sources, simulation sources, create file, SystemVerilog, test benchmarks. Okay. Yikes. Create file. No, sorry. Yeah. No inputs, no outputs. Okay, now it should be here. Yes. This file is here because it's a source file, so I think it automatically it is automatically included everywhere. But let's see. So now it should be here. Yep. Nice. So we don't need to include anything in here because it's a top level. I will write it. Don't need any word code. It's top level. Declare logic signals to connect to the device under test. We use logic for everything in SystemVerilog test benches. Okay. So logic test bench A. No. Logic test bench B. Okay. Then we instantiate the module of the MUX. So device under test. Let's write it because I will forget about it. This is very similar to Vivado, except that here we're using dots. A is TPA. Okay, it's actually, I like the syntax, it's not bad. Dot B is test bench B, so we're just wiring them up basically. Dot cell is TB dot cell dot y is TB y. Then we need to close this. Okay. I don't like that it's not indented. Write the stimulus in an initial block. Okay, so the initial block is used to execute what you would put in an OS block, but just once. So okay. GBA. Okay, I can use equal, which is great. 1, it's a bit, and it's 0. So let's put A to 0. Let's put B to 0 apparently. Let's put select to 0. Yes. Then we wait for 10 time units, and the time units are nanoseconds. Then here we update A and we put it to 1. And then select with 1 should select B. So wait, let's update B then to 1. And then let's wait other 10 time units. Try the more test cases here, change TB, TI, and TB to different values. Add 10 delay after each change, you can see it in the waveforms. And maybe, yeah, we can also update select to see if something changes. Let's put select to, no sorry, select is 0 here. Let's put select to 1. This syntax is a bit confusing, but it's also powerful. I meant the one to update, to set a signal, which is not a signal, it's a logic, to a bit value. Okay, so now we have updated the simulation. We should put it as a top level, I guess. No? Okay, apparently not. So let's try to run the simulation. Okay, so when A and B are 0, select is 0, the output is 0, which makes sense. Then A goes to 1, but select is still 0, so the output also goes to 1, which is correct. And then when select goes to 1, it selects B, which is 0, so this goes to 0, which makes sense. I want to try now to run the synthesis and run a post-synthesis simulation so that we can see maybe a bit of the delays. So let's try to run the synthesis with maybe 4 jobs, because I don't want to or even 2 maybe, because I don't want to stress my laptop, which is already doing a lot of things. And let's try. I think they already did the synthesis. Okay. Other apples. It's this one. It should be. Where is the? I want to view the. Design runs. Here it is. Okay. So now I can run our post-synthesis timing simulation. And let's see what happens. Here is the device where we can see actually now I'm not sure that it's going to work because we did not. Yeah, probably it didn't work, but let's see. No, it works. Okay, at first the output starts as an X undefined value, I guess, which is normal. Then A is set to 0, but before. Can I create another marker? Cursor, markers, add marker. Yes. No. Yes. So just after 5 nanoseconds, the value is set to 1. Which is something that you should consider if you're doing a digital circuit, because this creates glitches. Okay. Then here the select goes to 1, but just after other 5 nanoseconds the output goes to 0. Okay, cool. Very cool. Discard. Okay, this was actually super interesting. Where are the sources now? Sources. Yeah. So I guess after this we can really start building our RISC-V CPU. But before that, we need to do a bit of research. So for now, I'm just going to ask this question. Other than that, I tested the test bench and it was super good, super cool, super good. I am now ready to build my 32-bit RISC-V CPU. I think that on architectural choices and implementation ideas, tutorials. Okay. So first of all, I want to modify a bit my README. We can remove this because we did it. I can also remove this. So the CPU, I'm going to target where is the CPU is 532 the CPU. So let's create here some kind of subdivisions, like this. And here I'm going to put some resources that we are going to need. So just RISC-V. So we need to choose an ISA, instruction set architecture. Okay. Okay. So we are going to need probably going to need both the unprivileged and the privileged architectures. Because in order to make an OS, you need both privileged modes. I'm not sure if I can start from the unprivileged one and then switch to a privileged ISA. I think I should just start reading it. Wow, 700 pages. Oh, it's really got bigger. Instruction set manual, unprivileged mode. Yeah, I think we're going to target as the first one this RISC-V32I base integer instruction set. And after that we can move on to include bigger things. Oh, sorry, this should be a triple heading. need to retry here, I don't know what happens. What's the problem? Oh my gosh. I don't know what is happening. No. Okay, let's see if it works. In the meantime, I'll not read this straight away, but I will save this page because it looks full of useful informations, and I'm going to put it here on the readme. It wants to create a directory? What the fuck? No. No, don't want to make a directory. Oh my gosh. Yep. Okay, yeah, we can start reading the privilege file, but I'm going to be asking Gemini if I need to implement directly the privileged one or not. But let's try to start reading this. It's huge, it's a huge file. So these are the base ISAs, and then there are extensions. Cool. And I guess we're going to go with this RISC-V32i. Should be the base one, but let's see. Okay, let's move forward. Phase? No. Introduction. RISC-V is a new instruction set architecture that was originally designed to support the computer architecture research and education. We now hope it will also become standard free and open architecture for industry implementations. Our goals in defining RISC-V include a completely open ISA, real ISA suitable for direct native hardware implementation, not just simulation or binary translation. An ISA that avoids over-architecting, or implementation technology. An ISA is separated into small base integer ISA, usable by itself as a base for customized accelerators or for educational purposes, and optional standard extensions to support general purpose software development. Okay. An ISA supporting extensive ISA extensions and specialized variants. Both 30-bit and 64-bit address space variants. Okay. ISA with support for highly parallel multi-core or many-core implementations. Optional variable length instructions. Okay, that is good. Fully virtualizable ISA to ease hypervisor development. ISA that simplifies experiments with new privilege architecture design.
Mi dispiace.
What the fuck? Siri just activated itself. The RISC-V ISA is defined avoiding implementation details as much as possible, and should be read as the software visible interface to a wide variety of implementations, rather than as the design of a particular hardware artifact. The RISC-V manual is structured in 2 volumes. The volumes cover the design of the base and privilege instructions, including optional unprivileged ISA extensions. Unprivileged instructions are those that are generally usable in all privilege modes, in all privilege architectures, though behavior might vary depending on privilege mode and privilege architecture. The second volume provides the design of the first classic privilege architecture. Okay, my question is, if I do start using the unprivileged ISA, can I then include privileged instructions? What is it doing? Okay, sure. Okay, so I asked what is the reason on why we need this assigned keyword if this thing outside of an OS block is concurrent by itself, and it says that it's related to context, the historical context. In Verilog, the module body can contain many different things: continuous assignments, procedural blocks, modular instantiation, and initial blocks. The original parser designers require a specific keyword or a module name to begin every statement, so the compiler knew instantly what type of construct it was looking at, without having to look ahead at the rest of the line. I mean, okay. Okay, cool. Also, enjoy getting the test search working. Talking on a 30-bit RISC-V CPU is a fantastic project. If you want to build it from scratch, we should start with a solid fundamental architecture. The most common starting point is a single cycle architecture. No, I'm just going to go for a pipeline version, so let's write it. RISC-V 32-bit pipeline CPU. No, okay. A few questions for you. I want a CPU that is in a later stage going to be capable of executing a simple OS. So if I target, I want to target the 30-bit RISC-V architecture. Should I start with RISC-V 32i unprivileged or privileged? In general, if I start with unprivileged, can I then add easily the privilege mode? So let's see. We need a privileged architecture because we need a way to separate the OS from user applications. RISC-V defines machine, supervisor, and user modes. Okay. The ability to handle external events and internal features. Control status registers, virtual memory. You should absolutely start with the unprivileged RISC-V redo I-based integer instruction set. Okay. Building a CPU is an iterative process. If you try to build a CSR, trap handling, and the LU all at once, debugging will be a nightmare. It is easy to add privileged mode later. Yes, the beauty of RISC-V is its modularity. The unprivileged data path, so fetching instructions, doing math in the LU, loading stored data, is the core engine. Adding privileged features later is largely an additive process. You will add a new hardware block, the CSR file, parallel to your register file, and then we'll add logic to the control unit to say, if with an exception, stop the normal flow, save our state in the CSR, and down to trap handler. Okay, whatever. No, before actually, it wants me to build an ALU just straight away without even deciding what is the architecture, how it is structured, which is not what I'm going to do. Before actually doing that, I want you to tell me which are some questions I should ask myself now to decide the architectural choices which I need to make to create a 32-bit RISC-V core. Like, for example, Harvard. Oh my gosh. I don't know how hardware is written actually. Or von Neumann architecture. Pipelined, or else, or many other things. Actually, I'll tell him, create a file called plan.md where you put as much of these kind of questions that you think are great to ask, so that I can later answer them. Okay. I think after this I'm going to go for lunch because I'm getting really hungry. A RISC-V hardware platform can contain one or more RISC-V compatible processing cores together with other non-RISC-V compatible cores. Fixed function accelerators, various physical memory structure, I/O devices. Cool. A component is termed a core if it contains an independent instruction fetch unit. So if it contains an independent instruction fetch unit, it is a core. A RISC-V compatible core might support multiple RISC-V compatible hardware threads, or HARTs, through multi-threading. I think I should download this file because I want to take highlightings and other like how Firefox handles that. So probably I can put it directly into the folder, and then I'm going to add it to the git ignore. Yes, let's put it here. Yes, and now I am going to create a docs folder. For now I'm just going to put this here, and then here I'm going to put docs, and from here I need to remove something. So maybe I can do this. That nothing changed. Didn't work. What is the git firefly? Let's close this in the meantime. I don't understand. I'm going to ask another Gemini session for that, but not here. You cannot see it, but I'm going to ask. Why is my git ignore? My git not including the source files with this git ignore and the tree on the right. So let's see. In the meantime, yes, let's create this. Okay. The problem is that this, removes everything, and once it's removed, it's removed. This is also why we don't have this TCL file, I guess. Okay, we can do this then. Is it working? I have no idea. Wait a second. No, the plan is to be here. Okay. Let's see actually if it worked. If I go in here, no, it's not. It's still not working. What if I do this? No. Okay, I'm checking why it's still not tracking those files. I don't know what's the problem. Oh my gosh. Let me try to do this. Now it's working. What the fuck? Why? I don't understand. This is useless. Okay. Okay, now it should work. Let's see. Wait. So we updated git ignore and readme plan. Yes, TP mux. Yeah, close it. Mux and this XPR, which I'm not sure we need it, but whatever. I want to see the plan. The architectural questions help guide the design of your 32-bit RISC-V CPU. Answering these will help establish a fundamental structure of your hardware. Harvard, von Neumann. Instruction memory. Okay. Yeah, I'm going to need to answer these questions. Single cycle, multi-cycle, or pipeline? Okay, branch prediction. I need to study on those because I forgot everything. Okay, yeah, I will answer these questions so that they will also give context to the AI, which is going to help. And then I think that's it. So for now, I can push this code, stage all. Yeah, let's enter a commit, generated commit message. Let's see what it writes. If it does work. taking a long time. Initialize RISC-V CPU project and add MUX module. Update thread.me, just don't need to specify everything. Yes, okay, great, we can push. Great, so I think for today it's everything. It was really informative. We did a lot of stuff, and I'm gonna see you next time. Bye bye.